let us begin with the second lecture in this module 2. So, in the previous lecture we had discussed minimum energy point, that is the value of supply voltage VDD, which ensures a minimum energy operation, and we would also discuss the minimum energy as a function of activity factor, and in this lecture we would discuss the minimum energy point model, that is how the optimum VDD which ensures minimum energy operation is dependent on say supply voltage, on threshold voltage, on the switching capacitances, and also the overall area of the circuit. And then we will discuss how you can obtain for a given speed that you require, what is the minimum energy that you can obtain. And we will discuss the implication of system level decisions on the minimum energy point. So, in the previous lecture we had discussed that there is a minimum energy operation as you an optimum VDD which corresponds to a the minimum energy operation. So, this arises because in near threshold and sub threshold regimes, the time period of clock increases as you reduce the supply voltage, and that also increases the leakage energy exponentially as you reduce the VDD, but the dynamic energy keeps on reducing as you reduce VDD. So, this gives rise to an optimum VDD which ensures a minimum energy operation, and that turns out to be near the threshold voltage. That is why in low voltage operation near threshold operation is important. This is a value of VDD which is close to the threshold voltage. So, for low voltage operation, near threshold voltage operation is important. Now, let us discuss what is the implication of switching activity factor on this minimum energy point that we have discussed till. So, why should switching activity factor have an impact on minimum energy point? If the switching activity is lesser, dynamic energy consumption is smaller. So, it is leakage energy which would dominate. So, the components of energy consumption, dynamic or leakage, that which one would dominate depends on the switching activity factor, and therefore, the optimum is coming because of the interplay of these two components of energy. Therefore, the optimum VDD also changes with switching activity factor. So, the switching activity factor alpha changes E leakage and E dynamic. Therefore, VDD optimum or minimum energy point is a function of switching activity factor. So, what is this switching activity factor? Let us discuss briefly. Let us take this example data path. So, in this let us keep this input of NAND gate, one of the inputs of NAND gate at VDD permanently, and this input of the NOR gate is given an signal of this kind, where this signal is having a time period which is larger than the clock time period. Then there is no output switching whenever the input is 1, this input is 1, there is no output switching. So, for the inverter, the switching activity factor in this time. So, if we take an average of several clock cycles, the inverter would now have a switching activity factor which is smaller than 1. That is, if you take the dynamic energy of the inverter per cycle as being C inverter, that is the inverter input capacitance, then it would be C inverter into VDD square. But now on an average, so we need not consider all the clock periods which are occurring with when this input signal is VDD. We consider only those clock cycles which happen when this input is 0, because only then the inverter would switch. So, therefore, if the ratio of suppose this is T1 and this is T2, so this alpha would be T1 divided by T2, the time period. So, that is the ratio of clock cycles for which there would be switching in the inverter input. So, the switching activity factor for this inverter would turn out to be T1 by T2 in this example. So, the dynamic energy would get multiplied by this alpha switching activity factor. So, total energy is now this dynamic energy plus the leakage energy So, leakage energy is VDD into I leakage into the time period into this I leakage is now leakage per inverter, average leakage of an inverter, and W effective is the effective width of the entire circuit in terms of inverter size. So, that is in terms of inverter size. Suppose the inverter's NMOS width is and PMOS width is some beta times W. So, in that case we can characterize the inverter size in terms of the NMOS width W and say that this W effective is the effective width of the entire circuit when compared with that of inverter. Then what we would do is that suppose leakage current of the inverter has a certain value and suppose the leakage current of the circuit, the entire circuit has this value, then what is the value of W effective? Then this is inverse of this. So, what do we mean to say is that for the inverter this is the average leakage current and suppose the inverter has had a size instead of W, suppose the inverter has had a size some W effective times W. So, W effective times W, then you would have leakage which is equal to that of this I leakage circuit. So, in other words what we are saying is that this I leakage circuit is W effective times the I leakage of a unit sized inverter. This is unit sized. So, for a unit sized inverter where W of the inverter is 1 unit, it could be the minimum channel length 1 unit in our case. So, in the size of the inverter is 1 unit, it means that the NMOS width of the inverter is suppose 1 unit. So, it has a certain leakage current I leakage. So, I leakage of the circuit is W effective times that. That is how we define W effective. We will discuss this further later, but right now you can just keep it in mind that I leakage is that of here I leakage is I leakage of the inverter, W effective is the effective width of the entire circuit with respect to a unit sized inverter, okay, and that effective width is in terms of leakage currents, average leakage currents. Now, average leakage current means somehow you are taking all the inputs to be equally switching, that is they have equal probability of being 0 and 1. So, that average leakage into VDD, that is leakage power, into time is the energy, leakage energy, time period. So, as alpha reduces, if the switching activity factor reduces, that is if this in this example this period of the duration for the this input being 1 that is T2, if that increases then switching activity factor of the inverter would reduce. So, if alpha reduces, dynamic energy reduces, we can see that. And what is leakage energy? Leakage energy is flowing for the entire clock period, and so you can take an average leakage current. So, the leakage contribution, so leakage energy would remain the same because you are not changing the time period. So, leakage energy's contribution would remain the same. So, in overall total energy, leakage energy's contribution increases. So, now to reduce the leakage, so now to optimize, you need to, when you reduce the VDD, what you find? You increase time period T, okay, and you reduce leakage current slightly, you reduce this. So, time period T increases exponentially and therefore, total energy may increase. But if you increase the value of VDD supply voltage, you would find that dynamic energy increases, but time period reduces, and therefore, and that is an exponential reduction as we had discussed in the previous lecture. When you are operating in near threshold or sub threshold regime, it is an exponential increase in time period that you will find with increasing VDD. So, this would reduce significantly and therefore, the leakage energy would reduce. Dynamic energy may increase, but leakage as a square law, leakage energy may reduce exponentially because T reduces exponentially. So, overall you may find that the total energy actually reduces. This we will discuss more in better detail later. So, what we find is that as you may get minimum energy for an increased, relatively increased VDD if the activity factor reduces. So, the minimum energy point reduces. So, alpha likewise if the value of alpha increases, the minimum energy point may reduce. Yeah. So, this was a brief discussion on why the minimum energy point is a function of the switching activity factor alpha. So, we have considered a very simplistic case of this data path. The circuit could be quite complex. Nevertheless, this result that if you reduce the switching activity factor alpha in the circuit, the minimum energy supply voltage may increase a bit, it would increase. Now, let us derive the minimum energy point model. Now, let us discuss the minimum energy point model. So, what is the total energy? It is the dynamic energy plus leakage energy. So, let us write them down. Now, it is alpha C effective VDD square. What is C effective? That is the effective capacitance, effective switching capacitance. So, for this in terms of the switching capacitance of input capacitance of an inverter. So, in terms of input capacitance of the inverter, what is the effective switching capacitance of the circuit and how to obtain this effective switching capacitance, that we will discuss. So, effective switching capacitance plus leakage current. Leakage current is I leakage plus into VDD into time period as we had discussed earlier. Now, let us write down expressions for each of these. For leakage current, we can write it to be leakage of I naught. Now, that I naught exponential. Now, we are taking an average kind of leakage current. So, we would assume that the input voltage is VDD or 0. So, even when the input voltage is 0 for the P MOSFET, when V in of an inverter is 0, for the P MOSFET the source to gate voltage is VDD, and for the N MOSFET the drain to gate voltage, drain to source voltage is VDD. Likewise, when input is VDD, for the P MOSFET the source to gate voltage is 0, and for the N MOSFET the gate to source voltage is VDD, and for the P MOSFET the source to drain voltage is now VDD. Okay. So, when we write this leakage current, we are writing for either P MOSFET or N MOSFET. So, when we are writing for but the gate to source or source to gate voltage for N MOSFET or P MOSFET is 0. So, you would find this to be I naught into exponential VGS minus VTH. We are right now ignoring the impact of V out or VDS by NVT. Now, and we also have a value 1 minus exponential minus VDS by VT. Now, since VDS is close to VDD, you can ignore this term and you consider only this term. Now, what is this? VGS 0. If it is P MOSFET, it is VSG, that is again 0, and it is magnitude of threshold voltage instead of threshold. So, you could have written this as I naught exponential minus VTH by NVT. What about time period? Time period, as we had seen, is VDD into gate capacitance of an inverter divided by I naught exponential the current. So, what is the current? So, if we are assuming the current to be on current in this subthreshold or near threshold regime, then it is VDD minus VTH by NVT. Again, we are taking VDS to be average VDS during switching to be much larger than the thermal voltage, and that is how we are dropping the VDS term into something called logic depth. Now, what is this logic depth? So, for a given circuit, this logic depth is the number of stages in terms of an inverter. So, if the delay of the circuit is some T circuit, then and the delay of the inverter is T inverter, then this logic depth is given by T circuit by T inverter. So, the total time period is logic depth into T inverter. That is what we have done here. So, therefore, here you have this becomes alpha C effective VDD square plus I naught exponential minus VDD by NVT VDD square Cg W effective into logic depth. Here we observe that the threshold voltage terms in leakage current and in the time period they cancel out. So, the leakage component seems to be not dependent on the threshold voltage E leakage. Why? Because as you reduce the threshold voltage, time period, the delays would reduce, time period would reduce exponentially, whereas the leakage current would also, also the time period would reduce exponentially and leakage current would also increase exponentially. So, therefore, you would find that with reducing threshold voltage, the leakage energy does not change significantly. So, now if you want to optimize, if you want to find out the minimum value of energy, what is the supply voltage for which the energy assumes a minimum value. So, you just take a derivative d total energy by d VDD, that should be equal to 0 and that becomes 2 alpha C effective VDD plus 2 I naught exponential NVT VDD Cg W effective LDP. Now, you can minus I naught exponential minus VDD by NVT into VDD square Cg W effective LDP. So, this should be equal to, so you can write this as 2 alpha C effective VDD plus 2 minus VDD by NVT exponential minus VDD by NVT VDD Cg W effective LDP by NVT. So, now you can rewrite this as 2 minus VDD by NVT into exponential 2 minus VDD by NVT into exponential minus 2 by NVT is equal to 2 alpha C effective VDD by I naught W effective Cg VDD LDP exponential minus 2 by NVT. So, we have multiplied both the sides by this exponential minus 2 by 1 NVT. So, rearranging the terms in this expression, we would write it in terms of 2 minus VDD by NVT. Likewise, the exponent is this, but we introduce a 2 here. So, that is why we get an exponent of 2 here. Okay. So, what do we make out of this? One thing is that you have a negative sign here. So, the right hand side is negative. It means that VDD by NVT should be greater than 2. So, what we mean to say is that our work should not be valid, would not be valid for a value of VDD which is smaller than say 50-60 millivolts. So, all the expressions that we have used would not be valid when you reach a value of 50 to 60 millivolts. So, lower bound on VDD. The other thing is as you increase C effective. So, now let us write down what are the implications. C effective, that is effective switching capacitance is increased. So, what do we mean by increasing effective switching capacitance? That is if the circuit elements are increased, number of stages are increased or parallel paths are increased in a data path, the parallel paths are increased. So, you have more switching capacity, effective switching capacitance. What would happen? Dynamic energy should increase. So, if dynamic energy increases, we would like to reduce the supply voltage. So, that dynamic energy, so for minimum energy consumption, if you reduce the supply voltage, dynamic energy would reduce. So, if you reduce now the VDD optimum, dynamic energy would reduce and what would happen to leakage energy? You have reduced VDD. So, time period increases, but the leakage current reduces a bit. So, therefore, leakage energy would remain almost constant. So, what would happen to the, so you may find that you reduce energy, if C effective increases, then you may find that you reduce energy as you reduce the supply voltage. So, you may find that C effective increases, you may reduce energy for VDD optimum, that is minimum energy point reducing. Likewise, if the effective width increases, that is you have some, so you increase the say sizes of all the logic gates. So, in that case effective capacitance also increases, effective width also increases. So, suppose you increase only the effective width. So, in such a case what would happen to the minimum energy point? So, you have increased the leakage energy, but not the dynamic energy. Now, you want to reduce leakage energy. To reduce leakage energy you need to increase VDD, supply voltage, because when you increase supply voltage the leakage of the time period would reduce. So, if the effective width increases, you want to E leakage increases. So, to reduce E total energy you would reduce VDD optimum increases. So, time period reduces, E leakage reduces. So, that is the, so you would find that the optimum supply voltage which minimizes energy, that is minimum energy point, actually increases if the effective width increases. Likewise, logic depth, what happens with logic depth? If logic depth increases, then effectively the number of stages are increasing. Switching would happen in one of the stages in a data path. So, the switching energy does not increase, switching energy would increase only with so the effective switching capacitance would not increase. So, what would increase is the effective width. So, therefore, for when you increase logic depth you would find that this becomes a smaller value, it is a smaller negative value. So, if it is a smaller negative value then VDD optimum here it should increase. So, today we have discussed the minimum energy point, how it is affected by activity factor, and then we discussed how the minimum energy point is related to supply voltage, to effective switching capacitance, to effective width, and how it changes with these. And we will continue with this discussion in the next lecture, where we will understand more about the minimum energy point changes with system level decisions and what is the implication of system level decisions on minimum energy point, and also regarding the threshold voltage, what is the implication of threshold voltage on the minimum energy point. Thank you.